Welcome back to ECE 501B. Two more homework sets. One of those is going to be finished this evening. You'll need to submit that into the Dropbox. The next one is due in a week, homework number 8. And that's the due date for several different things. Homework 8, your project deliverable, and project deliverable number 3 is really a reflective paragraph, so don't forget to do that, but it doesn't need to be obviously as much time as you've invested into deliverable number 2. Deliverable number 3 is just kind of a discussion to me as to how you viewed or how you view the project and what you've learned from that experience. The final exam is on a Tuesday, and it's 2 weeks from yesterday. It's the 11th of December, and it's from 6 to 8 p.m. I had an email from a student wondering about Chapter 9. Chapter 9 you're responsible for, consistent with what we covered in Chapter 8. We talked about Chapter 8, certain things in Chapter 8 with respect to complex vector spaces. Chapter 9 deals with real vector spaces. You should look at the parallel sections in Chapter 9 that parallel the material we covered in Chapter 8, and that you should be ready for the final exam. Chapter 10 we're not going to cover a lot, but we will talk about the trace and the determinant. Then we will get into the Moore-Penrose Pseudo-Inverse, and if you recognize that name, that's because it was one of our resources in the course material. I think I gave you the first 4 chapters of Road to Reality written by that second author, Penrose, and that we will talk about today in terms of how do we create an inverse of an operator that may not be, or maybe even a linear map. It may not even be square. So how do we create a pseudo-inverse for that particular map? We might cover principal component analysis. It depends on how much time or how accommodating the time is for us today, but I may simply post a previously recorded session on PCA, or principal component analysis, after today's material, so look for that in D2L. Next week, the last week of the semester, we will begin the second half of the class. No, but we will move into the second text of the class, which is Frank's, and that's thinking about these concepts in infinite dimensions, and we'll try to motivate that with something that we're familiar with, which is Fourier analysis. We'll talk about then these infinite dimensional vector space ideas, or signal space or function space, via the Fourier analysis, and hopefully you're comfortable a little bit with the Fourier analysis. So the final exam will be the entire first text. It may not be all of the sections, but it's going to be consistent with whatever you are seeing during lecture and on the homeworks. So if I haven't covered something that actually is covered in the homeworks, that will be topic-wise expected of you to know for the final exam. The question was, is the final exam up to Chapter 10? No, it includes Chapter 10. So the final exam topic-wise is Chapters 1 through 10 of the yellow, well, the second edition was yellow. I apologize. So the third edition of Axler. So I don't remember the color scheme. Maybe I'm way off on that. So I'm not sure that answered your question. PCA, that might be helpful if somebody's working on that as a topic for their project, but it also is helpful, I think, to start to understand some of the connections of what we've talked about in this class with applications. So in that sense, maybe PCA may not be directly covered, but I could give you some new topic on the final, meaning you need to be able to figure that out based on the foundational work that we've covered in the class. And so now looking at that through the lens of what we've covered so far, that's what I want to sort of give you a feel for today. Okay? So let's look at Chapter 10, which now we can talk about a determinant. Since we're doing linear algebra right, we're now talking about the determinant of an operator or a matrix in the last chapter of the linear algebra text. So here, let's now look at trace and determinant of an operator. So if we now have, if V is a drugstore, no, is a complex vector space, not CVS, but C period V period S period. If V is a complex vector space and T is a linear operator on that vector space, then we can define the characteristic polynomial to be as Q of Z is equal to Z minus lambda 1 with a power of, on that factor, D sub 1, and we've talked about what these D sub j's mean. Those are basically the dimensions of the null spaces associated with each of these eigenvalues, lambda 1 through lambda sub m. Z minus lambda sub 2, D sub 2, on up to Z minus lambda sub m, D sub m, and that actually leads to, based on the Cayley-Hamilton theorem that we talked about last time, if we now use that linear operator as the argument of this polynomial Q, now we can have this operator as a polynomial operator. Or we now have this is t to the n minus lambda 1 plus lambda 2 plus lambda sub n, t to the n minus 1, and in fact this coefficient is the trace of our operator t, and we'll define that in a minute if we aren't comfortable with that, plus dot 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 plus minus 1. So the very last term, the constant term, is minus 1 to the n times lambda 1, lambda 2, the product of these lambdas, and this piece is actually the determinant of t, and we're using the fact that little n is the dimension of our underlying vector space, capital V. So this particular statement relative to the characteristic polynomial, if you multiplied all of that out, then the coefficient associated with the n minus 1 term in that polynomial is actually the trace of our operator t, and the last term in that expansion, irrespective of this minus 1 raised to the n, that product of these lambdas is our determinant of that t. And now we want to connect or sort of illustrate the connection between these trace, these operators and matrices, and determinant. Let's just look at a very basic example. Suppose now that we looked at a polynomial that just has, or is just second order, and so we have two linear factors, z minus lambda 1 and z minus lambda 2. So that now if this is easy enough to visualize, we can do this in our head. This is now z squared. If we apply FOIL, have we talked about FOIL, or was that in another class? But apparently maybe this is later than when you went through school, but now I think some students in elementary or middle school or high school learn FOIL, first, outer, inner, and last, to form or to keep track of the four terms that fall out of this product. So if you hear me say FOIL, that's what I'm referring to. But in this case, we can say we have now lambda 1 plus lambda 2 times z as the coefficient of the first power of z, and then plus lambda 1, lambda 2. So there is a second order example. Little n is 2, and you can see that the power of the n minus 1, or the coefficient of the n minus 1 term, is the sum of the lambdas. The constant coefficient is the product of the lambdas. And that actually follows for a third order, fourth order, etc., if you multiply it out. And then you have the intermediary terms associated with what is between the n minus 1 power and the z to the 0 power. But here you don't have those because it's second order. Just as an example of connecting this more general description of the characteristic polynomial and a second order example, just to get our feet on the ground. The trace of this linear operator t is now what we had defined to be the sum of these eigenvalues of t, where we actually have to keep track of the multiplicities in lambda sub I. If they're repeated, we need to keep those in the addition or in the sum. This is now the sum of eigenvalues and that sum includes multiplicities. If lambda 1 is equal to lambda sub 2, you need to add those together in this sum. But now you might ask, but how do we compute that? Since I know that you enjoy finding the eigenvalues of a generic operator t, let's say on the final I gave you a linear operator that was fifth order, I know you would have a fun time finding those 5 eigenvalues. Because you now have the eigenvalue-eigenvector equation. We didn't do it by doing determinants, so now how do we compute? We would have to find those 5 lambdas and then sum them up to get the trace, knowing what we know now. Well, now I'm going to give you a more direct way of finding the trace of that linear map. But how to compute TR of capital T. If we have the matrix representation of that linear operator T, then in fact the trace of T is equal to the sum from I equal 1 to n of the diagonal terms in the matrix representation of T. And so the trace is quite easy to find. You can find that by just adding the diagonal entries of your matrix representation of that linear operator without having to find those 5 eigenvalues. But it will equal the sum of those 5 eigenvalues. Here are some matrix facts. suppose we have a matrix that's n by n. It's square. The trace of that matrix which I'm also maybe writing as just TR of A, is simply the sum from I equal 1 to n of A sub II. And in fact, that's equal to the sum from I equal 1 to n of the lambda sub I. Or let me change this index just so that it's clear. So you wouldn't have to find the eigenvalues. You could just work with the matrix representation of the linear operator and sum the diagonal entries, and you have the trace. So for any matrix A. Question? So that's true for regardless of your basis. Correct. So the question was, does it depend on the basis? Now it does not. I mean, the coefficients will vary, but their sum will be the same, consistent. Yes? So now, no, A does not have to be in upper triangular form. So A is just a generic matrix. By definition, the trace of A is the sum of those diagonal elements, and in fact, that's also equivalent to summing the eigenvalues. That's the trace. The determinant of a matrix which I might just denote by single vertical bars on A, or I might say the determinant of A is now equal to the product of those lambdas. And if you recall from a linear algebra, the determinant expression is kind of involved, but here we're saying if you do have those eigenvalues, then you can write down the determinant of that matrix as the product of those eigenvalues. If, or for, let's say, for this linear operator T on V, the determinant of T, which we can call little det of T, is the constant term in the characteristic polynomial times minus 1 to the dimension of V. So if you found the constant term in the characteristic polynomial, the determinant of T could be found from that by scaling it by minus 1 raised to little n, where little n is the dimension of capital V. If we were dealing with complex field of numbers, then the determinant of T is consistent with what we just defined. This is now from I equal 1 to n of lambda sub I, where that lambda sub I, again, we need to include the multiplicities. So now let's say that we're playing with knowledge of these eigenvalues. How can we sort of use that to our advantage, or with these determinant expressions, or now that we know what these determinant expressions are are associated with products of eigenvalues, no matter what the field of numbers are or how they exist. Proposition 24 says that an operator is invertible if and only if it has a non-zero determinant. Remember, the determinant is the product of the eigenvalues, and now we're saying if that product is not equal to 0, then that linear operator can be inverted. If we find that the determinant is equal to 0, and so now we multiply all of those eigenvalues out if we have it, and if the product becomes 0, then we go, oh, we don't have an inverse if you were asked to find the inverse of that operator. Proof. Remember, an operator is non-invertible, meaning it doesn't have an inverse, if and only if it has a 0 for an eigenvalue. That was an earlier result. And now, in both of the cases, either complex or real, we now know that the determinant of this operator t in fact involves a product of eigenvalues. So that now, if we form the product and any of those is equal to 0, the product's going to be 0. So that now allows us to say that here's this if and only if relationship. If we wanted to check or decide yes or no, is this operator invertible, and somebody hands you the eigenvalues, if one of those is 0, or if you find the determinant, maybe they just say, oh, the determinant is 0, then you know that operator does not have an inverse. Thus, the determinant of t is equal to 0 if and only if there exists one of the eigenvalues equal to 0. Let's now look at another way to find, based on some of these facts that we now have. Let's put them together to see if there's a way that we can determine a way to find the characteristic polynomial. If you give me the eigenvalues, then and their multiplicities, you'll be able to create the characteristic polynomial. That's z minus lambda 1 times d sub 1, or raised to the d sub 1 power, etc. Here's an observation or fact. For t being a linear operator v, and if we now have two scalars, lambda and z, from our field of numbers f, then we can make the following connection. Lambda is an eigenvalue of the operator t if and only if, that's a two-headed arrow, if and only if this scalar, z minus lambda, is an eigenvalue of zi minus t, that operator. Z, remember, is a scalar, and I is the identity operator. Now, if somebody tells us, oh, and and I'm assuming that V is an eigenvector associated with lambda. And we're going to use that in the justification. But here, all we're saying is if somebody tells you or hands you an eigenvalue of this operator t, then now they can say, well, I'll give you another scalar z, and you can form a new operator, zi minus t, and now I can tell you what one of the eigenvalues is going to be of that new operator. It's going to be z minus lambda, that scalar. We put on our 2-year-old cap and say, why? So let's now verify that or convince ourselves of why that's true. Suppose we look at zv. That's now a scalar times a vector v minus t, the linear operator, times that same vector v. That, we know, is equivalent to ziv minus tv. Haven't done anything there. I've just introduced or inserted the identity operator between the scalar z and the vector v. But now let me remind us or explain that we're assuming v is an eigenvector of t with an eigenvalue lambda. That now allows us to rewrite this a little bit different and say, oh, via the eigenvalue-eigenvector relationship, TV is equal to lambda v. So I haven't done anything there. But now let me work with this last two expressions on the right-hand side of that equality. Meaning, let me now drop down an equivalent expression for both of those sides of that equality. And this one is going to be pretty easy. Let me just remove, again, that identity map or operator so that this says, oh, I have zv minus lambda v. But that I can just factor out the scalar, common scalar from both terms, and I have z minus lambda times the vector v. What happens here on the left hand? Well, now I can factor out z times the identity operator and t from that vector v. Or I can now say, oh, this is zi minus t v. So that now I have zi minus t v equaling z minus lambda v. And I think that you can see, well, here I'm using right there, that's using the assumption that v is an eigenvector of t, and this piece really is just saying that that's my general notation or structure of an eigenvalue-eigenvector equation. I have an operator, which is now a scalar times I minus t, and it operates on a vector, but it just scales along that same direction by a scalar, where that scalar is z minus lambda. So this is, again, just the eigenvalue eigenvector equation. Again, that required v to be the eigenvector associated with the eigenvalue lambda of t. That was if v is an eigenvector of this linear operator t. So now I have shown, hopefully, that if somebody hands you an eigenvalue of an operator t, then they can create a new operator zi minus t for a scalar z, and you now know what the eigenvalue, one of the eigenvalues will be for that new operator. Let's now see if that helps us in any way make connections with this characteristic polynomial that we've been talking about. The above facts or the above fact lets us compute the characteristic polynomial of the operator t via the following theorem. Which is Theorem 25 in Chapter 10. If we have an operator t on this vector space V, the characteristic polynomial of t in fact equals the determinant of zi minus t. That's the theorem. So if somebody wanted to compute the characteristic polynomial of a linear operator without having to go through the computation of the eigenvalues, that's how we talked about it at the beginning of class. We said, oh, the characteristic polynomial, we can just say, is made up of all these factors. Z minus lambda 1. Let's say all our d's are 1. Z minus lambda 1 times z minus lambda 2, etc. That required us knowing lambda. Now, this theorem, we don't need to. We just have to compute the determinant of this polynomial operator, where z is now a polynomial. I'm sorry, z is a variable that's scaling I. Let's see how we can justify that. And we're actually going to use this if and only if relationship. Yes? So z is a scalar, but it's a variable. We haven't really said anything about what it is in this theorem. We haven't called it a fixed scalar. Z is now a variable. But it's a scalar variable. And z is going to scale this identity operator. Yes? The question is this easier or harder than the definition involving the eigenvalues, I assume is what you're meaning. Now, it really may depend on the situation, but this gives you another way to compute the characteristic polynomial. If somebody hands you all the eigenvalues, then no, this won't be easier to compute the determinant of this variable polynomial operator, or this operator that depends on a polynomial. Obviously, the variable is scalar, but still it gets pretty messy depending on the dimension of your vector space. So either one is going to be, if I gave you an operator that was 10th order, you probably wouldn't be happy trying to find all 10 eigenvalues by hand. Likewise, you probably wouldn't be happy trying to find the 10th order determinant. But here we're probably dealing with third order and second order, and then it's pretty clean, or a little cleaner. So here's the proof. We know that. How do we find the determinant of t? How did we say we could do that? just the product of all of the eigenvalues of this operator t. So this is now the product of product of lambda sub I equal 1 to n, where these are lambdas are the eigenvalues of this, let's say, matrix representation of t, which is A. Or they could be the eigenvalues of t. It's however you want to compute them. But now what do we also know? We know if we have the eigenvalues of t identified as lambda sub I, now if I said, oh, compute the determinant of zi minus t. Now you know the eigenvalues of this operator zi minus t. Those are just z minus lambda sub i's. So just form the product of those. So this is now going to be the product of I equal 1 to n of z minus lambda sub I. But what is that? Well, that was just how we defined the expression for our characteristic polynomial. We said that that was z minus lambda 1, z minus lambda 2, z minus lambda sub n. Here I'm going ahead and just, if they're multiples of these eigenvalues, they're included in all of these lambda 1, lambda 2, lambda sub n's. I'm not worrying about multiplicity here. And this is how we defined the characteristic polynomial. So now we have another way of finding the characteristic polynomial. We can say now just find the determinant of zi minus t, and this is a two-step proof or verification of that being true. Based on what? This if and only if connection of the relationship between eigenvalues of t and z minus lambda being an eigenvalue of zi minus t, and the fact that the determinant of an operator is the product of its eigenvalues. So this now allows us to finish the proof. Suppose, let's just look at some examples. Suppose that we now have t that's not how we did it, is it? We say something like that. P is a linear operator on V. V is now some two-dimensional vector space where the field is either real or complex. Suppose that now somebody gives us a particular linear operator, and suppose they say that T operating on a vector z1, z2 produces z1 plus 3 z2 for the first component of the output vector, and minus z1 plus 4z sub 2 for the second component of that output vector. Now we should all be very comfortable writing down the A matrix, where I'm now defining the A matrix to be the representation of that linear operator. What does that look like? It's square. It's now mapping a 2 vector into a 2 vector. And what are the elements in that matrix? Our top row is 1 and 3, and our bottom row is A self-adjoint? No, it would need to be symmetric, wouldn't it? If we took the transpose, it would have to equal itself. So this is just a generic operator, T. What if we now, here, this is not too difficult to compute. If I now find the characteristic polynomial based on the formula that we said, I can find it by taking the determinant of this matrix, zi minus a, where z is a scalar variable. Or this is now the determinant of z scaling the identity matrix in a 2 by 2 space minus a or if I now, those have to be compatible or consistent to be algebraically combined, which I'm doing if I'm subtracting one from the other. Now I have z minus 1, I have minus 3, I have 1, and z minus 4 for my matrix that depends on this variable z. The variable is a scalar variable z. But now, for a 2 by 2 matrix, I'm hoping we're comfortable with finding the determinant. Yes?
We can do it the other way, right? Like a minus zi.
So you could do this. The question was, does it matter how we algebraically combine? It could be a minus zi, and that would be equivalent. It just kind of depends on what you're feeling like. In this case, I wanted to subtract a from zi. I usually think of it in terms of zi minus a, the determinant. Here we simply form the product of the diagonal and subtract the product of the off diagonal, and that will be our determinant. Or we now have z minus 1 times z minus 4 minus 3 times 1. Or we have z squared minus 5z plus 4 plus 3. Or we now have z squared minus 5z plus 7. But based on what we have learned already relative to characteristic polynomials and their relationship to eigenvalues, what do we know from just finding this? Would this help us find our eigenvalues? Would this be maybe an easier way than trying to find the eigenvalues in chapters 1 through 9? Now we know that what is 5? That's the trace. That's lambda 1 plus lambda 2. So now what is it based on what we had said before? Let me see if everything is consistent. So now we did it here with the minus, and in the second order we had it with the minus. So now the sum of lambda 1 plus lambda 2, the sum of the eigenvalues is the trace, wherever I am, so that now those eigenvalues need to sum to 5. And we only have 2 of them. And what else do we know? What's 7? Now we have 2 equations and 2 unknowns. We could find those lambdas. That might be easier than saying, oh, I have this eigenvalue-eigenvector relationship. When is this lambda going to be satisfying these 2 equations? For what values of lambda? So it's another way of finding relationships for these lambdas, now that we're in chapter 10, doing it right. So we now have our characteristic polynomial, q of z, is z squared minus 5z plus 7. And we also know that the characteristic equation, which is the characteristic polynomial set equal to 0 solving that finds our eigenvalues as well, right? So we could find the lambdas by finding the values of z that force this to be true. But based on what we had last time, can you tell me anything, last time being the last time we were in class together, can you tell me anything about Q of A? This polynomial applied to the matrix A. If we now use or replace z everywhere with A, the matrix, I can write that down. That's a squared minus 5a plus 7i. And a is our 2 by 2, so I is 2 by 2. What do we know has to be true about that? Does that help? Charles Hardy? No. Kaylee Hamilton? What does that tell us? That tells us that that is the zero operator. So we know that the matrix A satisfies its own characteristic polynomial. And this now, if you didn't want to square A, for example, you could find it as a linear combination of A and the identity matrix. Now if we use that a squared minus 5a plus 7i equals 0, we can now say, oh, A is actually equal, or I'm sorry, A squared is equal to 5a minus 7i. So now we just scale A by 5 and subtract 7's on the diagonal, and now I can hand you A squared without saying row times column, first row, first column, first row, second column, and doing 4 multiplications. Might be more straightforward. What do we also know? What if I now handed you this and said, okay, what's the trace of A? Well, based on what we said A was and how we can find the trace of A, that's pretty easy, isn't it? We just sum the diagonals. So from our formula, this is now A11 plus A22, which is 1 plus 4, if I'm remembering what those were. Or now we know that that's equal to 5, but that's also equal to lambda 1 plus lambda 2. So we could now find this without computing that determinant of zi minus a. We could say, oh, let me find the trace of A. What about, what else do we know? We also know that lambda 1, lambda 2, the product of the eigenvalues, is equal to the determinant of A. And the determinant of A, what was A? 1, 3, minus 1, 4. And it's not too hard to find that 2 by 2's determinant. This is now 1 times 4 minus 3 times minus 1. Or now we know that the product of eigenvalues is equal to 7. And we found that without having to compute this characteristic polynomial and relate those to the constant term and the coefficient of the n minus 1 term. I know you want to go home and just make sure everything is consistent, so how would you do that? Just go home? You could use this, right? You could say TV is equal to lambda v. This is our eigenvalue. That was the incorrect answer, by the way. Eigenvalue, eigenvector equation. But at this time in the semester, it was a pretty good answer. Eigenvalue eigenvector equation. That now says that z1 plus 3z2 is equal to lambda z1, and the second row was minus z1 plus 4z2 is equal to lambda z2. And now you could say, okay, what values of lambda cause that to be true? That's your exercise if you want to go and see if you can now convince yourself that the lambdas from this have to be consistent with these trace and determinant expressions that we just...
Is it 2.5 plus or minus square root of 3j?
Pardon?
Is it 2.5 plus or minus square root of 3j?
The eigenvalues are actually complex.
So is it analysis?
Pardon?
2.5 plus or minus.
So now if you compute this, if you do this, if my math was correct, you could say that lambda sub 1, lambda sub 2 was equal to, what did I say? 2.5 is what you're saying, 5 over 2 plus and minus j square root of 3 over 2. Those are the eigenvalues. I've now given you the answer in the back of the book. You can now go home and check to see if my algebra was correct. But that looks a little odd because what? You know the product has to be a real number, 7, and their sum needs to be 5. And that's easy to determine. But that also might convince you that if you do have real coefficients in your characteristic polynomial, your eigenvalues have to appear in complex conjugate pairs. So the fact that we had our characteristic polynomial of z squared minus 5z plus 7, those have real coefficients. Well, the only way we're going to have real coefficients is to have, if we have complex roots, is for them to occur in complex conjugate pairs. That's kind of a justification by an example. That's now trace and determinant. Let's move on to pseudo-inverses, because we have a lot of tools now to use or to work with. Let's look now at the Moore-Penrose pseudo-inverse. Let's try to motivate this. Suppose that we have a map a linear map in some vector space. And this could be a measurement system. Suppose we have a map from capital V vector space to capital, let me correct that so that maybe I'm consistent with my notes, U to V, capital U to V. And suppose that now we have M as our output vector mapped through this linear map T. M is the result of mapping W through this linear map capital T. And let's just say with W coming from the vector space U, and let's say that that's now a finite dimensional vector space of dimension capital N. For some reason I'm going to capital now instead of lowercase, but that's now Nevada, big. And let's say that M, our output vector, lives in a finite dimensional vector space of dimension not necessarily the same. Let's say it's capital M. So that now maybe somebody says, oh, here are a bunch of measurements M, and here's the linear relationship, but I don't know what W created those. And now we want to try to infer or estimate what is W, what was the input that came through this channel, let's say, and gave us M's. So we wish to use this output vector M to infer something about the input vector W. Here's our question. What is the best linear method for estimating W from M? And let's just, for notational purposes, let's say that W hat is our estimate. W hat is what we will define as our estimate of W. We've been pretty vague in how we set this up, so let's just say the answer, it depends. It depends on the dimensions of M and W, and it depends on the rank, or the number of linearly independent rows or columns we have in that linear map T. So let's look at some of the cases for answers. Answer 1, let's say, A1, if let's say that our input and output vector spaces are the same, and that means that T is a linear operator on U, and let's say that that linear operator is in fact full rank, meaning all of the columns are linearly independent in the operator T. Under those conditions, then the best estimate of W is in fact exact, meaning W hat, we can simply invert that operator T and apply that to M. Somebody gives us little m, that vector, and they say, what's W hat, or what's W? Well, under these conditions, if the input and output vector spaces are the same, and the linear operator is full rank, all of those columns are linearly independent, it's an invertible operator. It's surjective, it's injective, we have that result, that all three of those conditions are the same. So now we can invert that operator, and what was M? Well, M was defined to be TW. Now we apply the inverse of T to T, and we see that, oh, W hat, in fact, is W under those conditions. What's another answer? Suppose answer 2 says that we still have the input and output vectors being the same, but now let's say T is an operator, linear operator on V, But now let's not assume that it's full rank. Is not full rank. What does that mean? Picture-wise, we can go into the clouds again, can't we? We can say, oh, here's our input space, but that's also equal to our output space. But now, if we go through this map T, we might actually have many vectors in the input vector space that actually map to the same point, because we have a non-full rank operator T. Or we could say that T can map many vectors to one vector. Or what's another way of referring to that? The columns of T are dependent, aren't they? Linearly dependent, and that means we can get non-zero vectors that map to the zero vector. We could linearly combine those columns with non-zero coefficients to form our non-zero vector that would then map to the zero vector. Or that means that we have a non-injective map, a non-trivial null space, which says then that we have no inverse and it's not surjective. It's non-surjective. So here we have many vectors in our input space map or mapping to the same vector. Which is another way of saying non-injective. So that maybe introduces Q prime, another question. Q prime, so we could have many W hats giving us the same M. So which of those W hats do we pick? Which of many possible W hats should we pick or use or select? Pardon? Just throw a coin, huh? Just roll the dice and say, you're giving me 10, let me just put a 10-sided coin together or a 10-sided die and pick one of those. Well, maybe that's not the one we want, but maybe what you do is you pick the smallest W hat. What do we mean by smallest? The one with the smallest norm. So that's maybe the one that we would pick. So pick the W hat with the minimum norm. So there's an answer. What are some other conditions for possible relationships between U, V, and W hat? And now, in all of those that we've talked about, the dimensions of the input and output were the same. What if they're different? Well, the same thing happens in terms of many to one under what case? Well, if the output vector space is less than the input vector space. This is also the situation of many to one and non-invertible, or it's underdetermined. The way I like to sort of think about this is if I now looked at the matrix representation of T that's going from a bigger input space to a smaller output space, now I can sort of think of the matrix in this form. It's what? Short and wide. We have a bigger input vector. This is our capital N, and this is now our output vector. This is our capital M. And M, we said, was less than N. So let's kind of make it an extreme case and say, oh, that means that we have a much shorter matrix rectangular-wise than it is wide. So this is now a non-trivial null space. This means that we have dependent columns in that collection. We have many, many columns relative to how many rows we have. And again, so this is now this many to one. Again, we could seek the W hat that has the minimum norm. So again, seek to find minimum norm solution. One more. What if capital M, the output, we have more rows than we have columns? What if M is bigger than N? Now we have an overdetermined situation, more equations than unknowns in a way. So unique solution should or could exist, but again, the matrix representation of T is not square. In this case, how do we find an inverse when the matrix representation of capital T is tall and narrow? It'd be nice if we could create a pseudo-inverse that we can use to all of these cases. The case where we have an inverse, the case when we don't have an inverse, and the case when these dimensions are not the same. So all of these situations can actually be addressed in the following way. All situations can be addressed by finding a reconstruction operator which I'll call capital P, that minimizes the error between what we measure, or what we would generate by using W hat, and what we measured relative to this linear map T. The error is now E is, let's say, the norm squared of T W hat minus M. So we want to pick W hat to minimize this error. The distance between TW hat, W hat being our estimate, and the measured vector M. And now that I have this norm squared, you know where I'm going. You know that you can write that as an inner product with T W hat minus M in both slots. So this error is now T W hat minus M, T W hat minus M in this inner product. So now if we want to minimize this error with respect to W hat, how would you do a minimization if you were in your first or second semester of college as an undergrad? Take some derivatives. So now we want to take the partial derivative of this error with respect to that vector W hat. But you can now clean this up by using all of our relationships on these inner products as far as the linear combination. So if we now form or find the partial of E with respect to W hat, that will actually be this equal to 2 times T dagger T W hat minus M. And if we want that to be a minimum, we set that equal to 0. So now solve this for W hat to force that derivative to be equal to 0. Meaning, now I have 2 times T dagger T W hat minus 2 T dagger M equaling 0. Just add, or let me divide out the 2. That's a common positive number. I can get rid of that, and now I can say, oh, T dagger T W hat is equal to T dagger M. Well, what do we know about T dagger T? It's a what we called positive, non-negative operator, and it's also square. So if it was positive in the traditional sense, no 0 eigenvalues, we could invert that bad boy and we would be done, right? We would operate on both sides with T dagger T's inverse, and now we have a way of writing W hat. Pardon? How do we know it's positive? That's a final exam question, isn't it? That's what we've been, I think, just discussing, that T dagger T is a positive or non-negative operator. So go back a few lectures and I think it's in there, isn't it? Yeah, so T dagger T is a non-negative or positive operator. So now we have T dagger T inverse times T dagger M. This is now what we want to use as our reconstruction operator. This is our P. P is now T dagger T inverse T dagger. And P is now what we will call is the Moore-Penrose pseudo-inverse.
What if P dagger T has a 0 eigenvalue?
So now what if T dagger T has a 0 eigenvalue? Then we have some issues, don't we? So let me try to make some notes for that. Suppose now, 1, if, let's say T dagger T, if it has a 0 eigenvalue, what do you know? It's not invertible, is it? So now this is positive or non-negative by the way we have talked about it in the past. But if that is non-negative, means we could have 0 eigenvalues, so it is not invertible. It's always square though, so we're good to go there. We can actually show that P equaling the limit as epsilon goes to 0 of T dagger T plus epsilon I inverse T dagger. So we can pick a small epsilon, multiply it by the identity. That's going to give us a non-zero eigenvalue. And it can be shown that this always exists and it gives us the minimum error, minimizes the error. So even though we might have 0 eigenvalues, we can pad that T dagger T with a scaled identity operator, invert that, and that's going to give us what we want. So this always exists and minimizes the error. Unfortunately, we're out of time, but I will finish this up with about another page after class. But we'll also see that we could form this P using singular value decomposition. And that we've learned how to do, or we know about the singular value decomposition. And it's not too hard to create P as a pseudo-inverse from the singular value decomposition. And I'll do that after class.